Railroad Seminar Series is sponsored by the National University Rail Center here at the University of Illinois at Urbana-Champaign. And on behalf of all of us, I want to thank the USDOT for their support of this seminar series. It's greatly appreciated by those of us here on campus, as well as those participating via the internet. Let me welcome those of you who are joining us via the internet today, which includes representatives from Boise State University, Patrick Engineering, Benesh Engineers, Amtrak, Genesee and Wyoming Railroad, LTK Engineering, TUV, Jacobs Engineering, BNSF Railway, Hanson Professional Services, Illinois Department of Transportation, and the National Association of Railroad Passengers Council, and a number of other organizations. And those of you who are dialing in via the internet who wish to receive PDHs for your participation, please send Emma Earnhardt an email with your information as described in the email announcement for this seminar. High-performance concrete with early strength development is the material of choice in the fabrication of prestressed concrete railroad ties. Its higher strength results in significantly higher values of the elastic modulus and increases the rigidity of the crosstie, leading to higher amplitude stresses and stress gradients, and eventually to premature cracking and deterioration of the crossties. The development of high amplitude stresses and the corresponding distribution of the stress field within the crosstie appears to be a common underlying cause of the most critical issues that affect crosstie performance. Dr. Rizos and his colleagues have developed a new high-strength concrete that exhibits low elastic modulus and can be used to fabricate crossties with improved performance, and that is what we'll be discussing in his seminar today. Dr. Dimitris Rizos is an associate professor and director of the Advanced Railroad Technology Group and the coordinator of the Railroad Engineering Program in the Department of Civil and Environmental Engineering at the University of South Carolina. He specializes in structural engineering and mechanics and has significant experience in consulting engineering as well. His academic and professional interests are in railway and highway infrastructure. He has expertise in development of computational methods for problems in wave propagation, soil structure interaction, soil and structural dynamics, and transient analysis of multi-phase media. He also has experience with analysis, design, and inspection technologies and assessment of railway infrastructure and high-performance materials. He has authored more than 90 technical publications in journals, books, research reports, and various conference papers. He serves as the vice chair of the American Society of Civil Engineers Rail Transportation Committee and is also a member of the TRB Track Structure System Design Committee and the AREMA Education and Training Committee. Please join me in welcoming Dr. Rizos, who will present the William W. Hay Railroad Engineering Seminar entitled High-Strength Reduced-Modulus Concrete for Prestressed Concrete Railroad Ties.
Thank you, Chris. It's an honor and a pleasure to be here and discuss the activities at the University of South Carolina related to rail and, of course, the most recent project that we're working on, and also have to acknowledge the contribution of the RailTech group in this project. It's real nice to see familiar faces, new faces, and all kinds of personalities. And by the way, you know, we have 4 types of personalities in the world. Right? When you stand in a tunnel, you have the pessimist who sees darkness at the end of the tunnel, right? And then you have the optimist who sees the light at the end of the tunnel. You have the realist that sees the train coming. And then you have the train engineer who sees 3 fools sitting on his truck. So on this positive note, here's a quick overview of the university. We have 8 campuses, more than 45,000 students. The main campus is in Columbia, South Carolina. Beautiful places, smiling faces. Those of you who joined the JRC conference last year, we hosted it. We're very proud of you for being there. So 14 schools. It's breaking up, I think. And we have more than 300 degree programs, 30,000 students in the Columbia campus, and approximately 1,500 faculty. In our department, we have the main areas, traditional areas: transportation, geotech, structures, water resources, structural engineering, of course, and railroad engineering, which is the latest addition to our program.
battery.
Maybe the battery?
Use this and we can replace the batteries. And
Oh, it's a battery phone.
shouldn't be.
So the objectives. So the objectives were to establish a national recognized research and education program in rail engineering that is a nucleus of excellence within the department in USC and support the industry and promote railroads both in South Carolina and the US. So this is our team, a number of faculty from different disciplines, electrical engineering, mechanics, mechanical engineering, and also we have a couple of adjuncts who are helping us with our teaching needs. And the way the rail group is organized is in 4 teams related to infrastructure, safety and operations, power signals, and education and student relationships. At this point, it's a growing program. The first and last groups are probably the more mature ones, whereas the safety operations and the power and signals are in a growing phase. And we do draw resources from within the university, other departments within the college, as well as across departments. ART group stands for the Advanced Railway Technology. And a little bit on the history. The seed was planted in 2008, and we used, at the time, a proposal to NSF on high-speed rail vibrations, develop methodologies to predict them, basically. To start doing... That's the train coming. No. So, can everybody hear me now? Better? I can yell if needed. So, in 2010 is a catalyst, the RIS symposium, and I think it was here in, it was in Kansas City, actually. And the JRC that year was also here at Illinois, where I was asking questions, where can I get material to teach railway vibrations? And one thing brought the other. Before we knew it, we embarked on a trip that was both adventurous but also very satisfying and rewarding. Fall 2010, the first course in high-speed rail dynamics was introduced in the curriculum. August 2011, the group was formally, officially formed. And we spent the first year establishing or developing our curriculum to develop a research program and get a little bit of funding in place. And 2015, since 2015, we have degrees, advanced degrees in rail engineering, Masters of Science, Master of Engineering, PhDs, as well as a graduate certificate, a 12-credit-hour graduate certificate that is offered online. So these are the courses, real quick, that are available and the semesters that they are offered. The first group of courses are directly related to rail engineering, so dedicated to rail engineering. The last group, the multimodal transportation systems management, risk analysis, and human resources, they have rail components, and all are part of a graduate certificate as well. We had over 250 students that have taken the courses in the last three years. As I mentioned, all these courses are offered online through our Apogee program, which is a program of graduate engineering education. It was probably one of the first programs in the country back in the early 80s, and at the time the operation was through videotapes. Nowadays it's live streaming and also available at any time on demand. And we also follow the model where the instructors don't have to be in class, so we do have remote delivery of lectures. So some of our research facilities, especially all the resources that we have that contributed to this project. Our structures lab, of course, doesn't compete with what you guys have here. I mentioned a couple of people had been to the lab about 20 years ago. And today, when I revisited it, I remembered why I was impressed at the time, and I'm still more impressed today. But we do have the capabilities for full-scale testing, some tie testing that goes on here. We have advanced for measurement systems based on digital image correlation techniques. We'll talk a little bit about this, that we use this both on large-scale specimens, but also for material testing. And of course, all the computing and modeling and simulation capabilities. So a couple of words on the digital image correlation system that we used. These systems are for 2D and 3D visualization and image correlation. And this was developed at the University of South Carolina about 30 plus years ago by Professor Mike Sutton in the mechanical engineering department. And of course, this technology moved into the industry. Correlated Solutions is a spin-off company out of this technology, and we're using their software and hardware for our testing. So it's a proven technology and has been applied to other industries like, for example, aerospace. Boeing is in Charleston doing a lot of work with measurements. The typical 3D system consists of 2 cameras and a computer setup, as shown here. It seems like a simple configuration, and it is. The procedure to analyze the data, of course, is what makes them different between different systems available in the market. What is a common thing here is a speckle that you need to apply to the surface that you need to measure. And of course, in this case, we have our sample. The cameras are looking at the sample. It's pretty much like the human vision. So you need to focus on the specimen. You need to keep the relative distance and position of your eyes fixed to a specific point. Otherwise, you lose the information. System is calibrated, and you get all the geometric parameters of the cameras as far as location, orientation, angles, and so on and so forth. And the way the procedure works, you have the 2 cameras taking images of the same specimen, same field of view, or at least very similar field of view, same object. So once the system is calibrated, the first set of images is taken, which is at the undeformed or the baseline state. Then you load the specimen. This is a deformed configuration. And then you correlate the 2 images. Pretty much you're tracking, not dot by dot, but in a statistical way, if I should say, a number of points within a square, and you move that across, and you try to track them in space. You compute the full 3D field. So we compute displacements in all 3 directions. Of course, you can post-process them and compute the strain fields. And this has been used extensively, has been validated in the lab. Here is one of the validation tests that I will show you today. This is a prestressed prismatic beam, and the objective here is to measure the strain surface, the strains that develop on the top surface of the beam when the strands are released. These are small strains, so you need an accurate and noise-free system to get the accuracy that it's required. The cameras are attached here on the top. Here's a detail of this. Here's 2 little tiny cameras, point gray camera shooting straight down into the face. Don't have to be perpendicular, as the restriction with the 2D systems. And we take the images, a set of images before the strands are released, so when the concrete has cured, and then cut them after the strands are released. Images are taken. In this test, we had a flame cut. We had to flame cut the strands, and these are the images that were obtained, where the top 2 strands were cut first, and then all 4 strands were cut. Average strain 110 microstrains in the first case, 180 in the second case. So here we're talking about real low strains. Now, if we plot the strain field along this center lines, line 1 that is shown here, the blue dots or triangles show the strain results. The solid line is an average. Bottom 1 is for stage 1 when the 2 strands are cut. Top 1 when all 4 strands are cut. So these numbers have been validated with strain gauge Measurements, of course, strain gauge are like spot measurements. And with finite element analysis of that same specimen, the solid line, this graph shows the longitudinal strain once again along this line as a function of location from the live end of the specimen. The solid line is the average, is what the finite element predicts at the constant section, whereas the dashed line is the average. I'm sorry, the dashed line is the finite element solution. The solid line is the DIC average value of this data here. And when we look at the displacement, the longitudinal deformation up to the midsection, this is pretty much what we captured here, we see the accuracy of the method. So now that this measurement technology was introduced, I would like to discuss the design of high-strength and low-modulus concrete crossties, which is a project that was funded by Federal Railroad Administration, and it's probably in its third year now. We'll touch a little bit on the historical background and how the idea came about, the hypothesis, material development and characterization activities, designed the fabricated prototypes and tested, qualified the product, and then through a series of investigations, we'll demonstrate the benefits of this product. So, some history on the project. Back in early 2000, we at the university was part of a team that we were investigating different concrete mixes to qualify them to be used as high-performance concrete in highway bridges in the state of South Carolina. We used local aggregates, and we used standard South Carolina DOT mixed designs. So based on the classification for high-performance concrete, the material is classified into three grades based on their different properties. And what we found out is that certain mixes, when we used aggregates from certain sources, it satisfied most of the criteria for grade 1 or 2, except the modulus of elasticity, which was quite low, 30 to 50% lower than what expected. However, the strength of that material was up there along with all other batches. So at the time, that material was rejected. And later on, when I started getting more involved with the rail industry and found out about the cracking problems in tires and so on and so forth, the idea came about, okay, here I have a product that can produce a more flexible structural member, get as strong as the concrete that it's already used. So maybe worth a while the investigation of using this material and find out how it performs in a system. Some graph from this old study, early 2000, about 10, 15 years ago. This top graph shows the modulus of elasticity, correlation of the modulus of elasticity with its compressive strength, and two groups of data. This group of data is the what we call unweathered aggregate, or the standard aggregate that it's used. These are granites, and this data here had to do with those batches that did not produce the modulus of elasticity that expected, and we found out that all these aggregate sources came from quarries where the granite was weathered. Correlation of the modulus of elasticity to the permeability, again, no correlation for weathered aggregates, and correlation as expected for the healthy material. So the hypothesis is that if we use such a material with a high strength but reduced modulus in a concrete tie, then we will be able to get a better load distribution within the tie. We'll get smoother stress gradients because of the higher flexibility, lower the stress amplitudes, delay the onset of damage, of cracking in that case, and improve the relative rigidity between the ties and the ballast. So some preliminary studies based on finite element analysis alone show that if we reduce the modulus of elasticity by 50%, then we can reduce the stresses from 15 to close to 50% at different critical locations related to the rail seat, center binding, and under the rail seat at the interface with the ballast. So here we departed on developing the material. Major time manufacture design. The only thing we changed was direct substitution of a material. We just wanted to change one parameter to make sure that what we will record in our studies makes sense, and we can find out why. So the specs minimum 28-day strength 7 KSI, and the strength at transfer 4 KSI. Did direct substitution of aggregates and considered 4 aggregate sources. CA1 is what is used by the manufacturer, and so limestone, and CA2 through CA4. These are the weathered granite from 3 different sources. Here is the material as arrived in the lab. Images of the aggregates, the 3 aggregate types. Students have a lot of fun, spend hours and hours in the lab producing those batches and taking measurements. And conducted standard ASTM tests on the coarse aggregate, the rock material, concrete, and the mortar. And in addition to the standard ASTM, we did some abrasion tests here at USC of Raleigh. And we will see the results in a second. So this is what we got from this first trial where we mixed the different batches. This is the compressive strength versus specimen age. And we can see that the limestone, which is the standard, is pretty much the lowest strength of all, especially at early times. At 56 days, the strength is about the same for all batches, so didn't lose strength there. And also notice here that these data are for multiple batches of the same aggregate just to test the repeatability. When we looked at the modulus of elasticity versus age, we see that the standard design modulus of elasticity follows the trend in the models that we're all familiar with. However, the weathered granites, the modulus did not pick up. Early times, you see a very small, relatively small difference between the modulus, but it seems that it looks like a good wine. The older it gets, the better it behaves or tastes. Okay, so we see higher reductions at later times of the modulus. And here's a correlation between the modulus and the compressive strength for the for our baseline, the standard mix, and the weathered granites. These data are plotted for strengths above 7 KSI, which is our design strength for the concrete batch, the minimum design strength. So taking a look at the properties now, notice that as far as the aggregates are concerned, voids density, relative density are all very comparable. LA abrasion test, the weather aggregates showed a higher degree of damage, if you want, of loss. So measured as between 33 and 46% as opposed to 27% loss that we had in the limestone. And I will discuss this in a second once I get down to the lapping test abrasion. The fresh concrete, same properties for all aggregates. For the hardened concrete, the compressive strength remains the same. Flexural strength about the same, but between 0.12 and 12 and 13% of FC prime. And elastic modulus, we've seen reductions between 37 and 50% just by using a different type of aggregate, the weathered aggregate. Now, when we look at the lapping test abrasion rate, please note that the weathered aggregate showed a better performance than the standard aggregates. So basically, the lower this number, the higher the abrasion resistance. This number is the loss of material after so many, or per minute of testing the samples, and I'm not going to go into the details at this point. But this finding contradicts the LA abrasion values. And the hypothesis here is that the weathered aggregates, they have fault planes inside the aggregate. So when you put them in the LA machine, all this banging and suffering, it breaks them apart. But when you have them confined in a concrete mortar and that mortar hardens, then the resistance is better than the limestone. So out of these batches, we chose the middle one, which shows a balance between modulus of elasticity, reduction in modulus, and LA abrasion to produce a prototype. So far we've produced concrete twice, one with reduced modulus, one in 2004 and then about 10 years later. Now we'll try a third and a fourth time, but this time we're not producing the mix, the plant will. So we produced ties in September of 2015 and August last year. This is the geometry. 8 7-wire strands is the reinforcement here, and this is at the plant the first time we visited. The cavity is filled with concrete, and here we do some surface preparation because we will be using DIC measurements to obtain transfer lengths, taking material for testing samples. This is the team with my students. I'm very proud of their work. And put this in a graph form again. We look at the modulus of elasticity versus age. We go to about 6 months now. And the trend continues. Concrete's produced third time, completely different conditions, not by us. And this is the concrete with the weathered aggregates. And in these numbers, we also have included one of the batches from our lab testing just to make sure that we are in the same range of values. Correlation, same findings as before. One thing that we tried in our second visit, we also produced a batch where we included fly ash in it. And this is very limited testing. We're just looking into different possibilities here, moving this work forward. So next, we will I would like to show you the measurements of the surface strains. This is the cavity or the bed, the pre-stressing bed, and mix one is the reduced modulus ties that we will be monitoring with DIC. So surface is prepared. We see the lighting. We do apply the speckle here with a roller, and the system is attached to the lift here. This is a detail, about 17 feet above the surface of the ties, a well-lit surface, and images are taken before strand release and after strand release. So this is the actual image that is obtained. I've just skewed it to make it a perspective and correlate it to the actual deformed surface that it was picked up by the system. So this shows the deformed surface, as recorded. Now, these color maps that you see here are superimposed on the images that were obtained from the cameras. The one on the left shows the longitudinal deformation. This is the live end, dead end, and for all these 4 ties, and the darker line represents the average of all, and we notice that some anomaly here. One would expect a little bit of a flat area where the transfer length is, and then straight line, and then flat area again. But we did see some sort of an anomaly. Then we looked at the out-of-plane deformation. So the deformation that is shown here is the actual lift of the surface of the tie in the vertical direction. And we noticed that in this lift, there was something that was holding the tie down. What you would normally expect if you compress the tie and you have some eccentricity in it, you will see a uniform curvature. But instead of seeing this, we picked up some catching there. Then we looked at the strains in the longitudinal direction. Okay, and although the live end looked as expected, you reach this plateau, you have the initial transfer length, and then you reach the plateau. At the dead end, something was going on. So the hypothesis here is that the form is catching the tie, and the form effects need to be also accounted when we do these measurements. So we tried different finite element models with boundary conditions where the form now, the boundary conditions of the form are included. And also, let me go back to the image with the pre-stressing bed. The strands run continuously through the bed. So when you cut these strands, the rest of the form, the entire cavity moves, and it moved by approximately 7 inches. We're looking at the beginning where the hydraulic unit is. So we can find the stiffness of the form and include these effects. And if we look at the tie without any form effects, we see this nice profile as expected of the strains at the tie underside. But with the form effects, we get a pattern that we say, I think we were right in our hypothesis. And if you look at the strain profiles as obtained through the DIC measurements and the finite element measurements, you see that there's something going on at this location and where the rail seat is. Again, direct comparison of the DIC color map with a finite element color map. We see these effects. Nevertheless, we were able to compute transfer lengths, and it seems that the high-strength reduced modulus ties did produce shorter transfer lengths than the standard ties, and also with a better coefficient of variation. And these measurements were not only from our DIC measurements, but were also measured by an independent contractor who was there at the time, using a different DIC system, and also Whitmore gauges. So product was qualified, followed all the standard ARIMA tests here. And for the rail seat and the negative and positive moments, here we're at the lab. DIC system also was used for such measurements. And the strand slippage was monitored. The slope deflection was also monitored in all cases. And we've obtained thousands and thousands of images. I'm just going to show you just a few here, just so that you can, everybody can see the benefits of using digital image techniques in strain field measurements. At 90 kips load, which we're approaching the design ultimate capacity, we see the cracks. Clearly can see the cracks developing on the tie. I just removed the color map, and these are the cracks indeed underneath. And we can do all sorts of things in actually measuring and tracking how these cracks open and close through the DIC measurements. Bottom line, the high performance, high strength reduced modulus ties all passed the qualification tests. The standard, there was one that marginally passed, and we were probably within the 1% of the rail seat moment positive value. Now, when we drove the test to failure, for the prototype ties, the pre-stressing strain is approximately 800 microstrains, 760, 770. And the crack is computed based on the flexural strength to about 320 microstrains, where for the baseline, so 500 microstrain pre-stressing and 220 microstrain for the crack flexural strength. So in order to crack the specimen, we need to monitor strains for the HSRM above 1100 and for the baseline above 700. Okay? Because remember, the DIC assumes a zero position when the pre-stressing is already applied. So whatever may be monitored or recorded as tension in the DIC, it's not really tension. It's we have to add the compressive stresses due to pre-stressing there. Testing that was conducted here at the Railtech facilities on the fastener pull-out and torque test, all the tie passed. Fastener uplift tests, the ties passed. And the fastening insert failure test, the standard and HSRM comparable strength actually Slightly higher, but I'm not going to claim it as a benefit at this point. What I would like you to notice, however, here is the cracking pattern. This is the standard, extensive cracking. This is the HSRM. We'll discuss the cracking patterns again when we do the benefits now. So now that we have a good product, how am I doing in terms of time? So now that we have a good product, first some variable support testing was conducted here at your facilities at Railtech. And for under full support and support conditions that will cause center binding. And of course, as expected, the HSRM is more flexible, so higher deflections, whereas the and a little bit higher deflections as shown here as a function of distance from the center of the tie. But very comparable otherwise. What is important to notice here is the cracking pattern. This is a standard tie where we see full width cracks through the tie, as opposed to the HSRM tie where you do have more cracks, but they are shorter and hopefully more shallow. We didn't have a way of looking at how deep these cracks went. But this is a typical behavior of resilient material or more flexible material as opposed to the full-length cracks that develop. So rail seat ultimate positive. I will show you the crack evolution, the cracking evolution here side by side of the standard and the HSRM, starting at a load of 45 kips. That's where that's below the first cracking. And monitoring the stresses. I apologize for the small fonts here. I'll try to read off the values. Here we're at 430 microstrains, 725 microstrain. Remember, we need 1100 plus for the HSRM to crack and 700 plus for the standard to crack. So 50 kips, still below the cracking load. The strains hover about the same values. Now at 52 kips, this jumped up to 820. So there is a crack. And if you take a closer look here with extensiometers and stuff, that crack is, we were able to pick it up. HSRM has not cracked yet, but you see higher strains that are spreading out. Now 57 kips, clearly stress concentration. Then we see two areas of high stress, and now the values here are still at 870, and no crack had been monitored. It's just the way the load is being redistributed. 60 kips, same story. Now the crack starts propagating, the load gets distributed, and this time. Now we look at the strains here. We jumped up to 4,000, 4,000. Here's a crack. Here's our crack. As the load progresses, we see two cracks, very distinct cracks in the standard, multiple cracks in the HSRM. When we plot this to the same scale, notice the opening here is much higher than the HSRM. So this axis now, this color map axis, going too fast there, were plotted to the same scale. All right. Then we tested the specimen in fatigue. There was no established procedure for this, so we did 3 million cycles, loading to 90% of the design load, monitor the strains. Then we induced a crack, loaded the specimen another 3 million cycles, and at the end we loaded the specimen to failure. So stage 1, no crack, 3 million cycles. This is the 0 cycle. This is at 13.5 kips load. 500,000 cycles, 838,000, over a million. So you see that the strain pattern does not change. No effects here of fatigue load. So no significant change in the strain field as load accumulates. No cracks observed. Stage 2, crack the specimen another 3 million cycles. So you can we can see here the evidence of the crack. As the load increases, the number of cycles accumulate, rather. Load is always 13.5. Notice that the crack propagates a little bit, but then it stops. And notice how the strains spread out. So we have load redistribution, which is an effect that's a desirable effect. This is what we would like to see. And then that's it. Nothing else happens to it, so the performance is maintained. So stage 3, loading to failure, 0 kip. Now remember here, this is already pre-cracked. Okay, this tie is already pre-cracked, so there is 1 crack at that location. At 6 kip, 8, the strains are still low, right? 290, which means that the crack is still closed because of the pre-stressing force. 12 kip, 13.5, 15 kip, 16.5. Still pre-stressing is high enough to keep the crack closed. Now we start seeing increasing strains at 20 kip, 10,000, and now 2 cracks at 22.5. And now 2 more cracks as the load increases. And yet another crack. So by the time it failed, it had developed 5 different cracks that had not propagated all the way to the top. So ultimate load, 34 kips. The standard, it was about 30 kips. Multiple shallow cracks indicate lower redistribution, and we had fewer but deeper cracks in the standard tie. Parametric studies through finite element analysis. I'm not going to bore you with the details of the model, but the findings, basically what we did here, we assumed we took the value straight out of our lab testing measurements, and we also applied some lateral load, L over V, 0.2 and 0.4. And the HSRM showed anywhere from 3 to 12% low stress. This is ongoing work. We just started it. This is still linear. We're moving into looking into the post-cracking behavior. So benefits, in summary. The new material maintains high strength, smoother stress gradients in tie and stress redistribution. Stress redistribution takes place after cracking. Amplitudes of stresses are reduced. Set of damage is delayed, means higher load to see the first cracking. And the next thing that we're looking at is better load distribution on the track because it's more flexible. So the hypothesis here again is that we're going to see a better distribution of the load on the track. So conclusions and some future work. We'll look at the residual strength, the post-damage performance. We'll do dynamic DIC measurements. We already started this with capturing images. I'm not going to show you an image because this is fairly new. We've done this the last month. We started the dynamic measurements. High-speed cameras, anywhere from the lowest high speed, which is 38 frames per minute, all the way to 10,000 frames per minute. Loading rates from 2 to 15 hertz on the tie and identify the dynamic effects. And effects on load distribution on the track. On our sand pit in the lab, we'll set up a track and do the measurements. And we will be installing these ties on a CSX line, heavy haul, curved track, and be monitoring their performance every 6 months for the next year and a half. So it's a good product. We're happy to see the results. We've applied for a patent on this, and it's a technology, the most important, it's a technology-based modification in concrete tie that improves the safety of rail service and maintenance operations without impacting the fabrication and cost. I'd like to acknowledge our sponsors, CSX, Rockla Ties, Federal Railroad Administration, sorry, as the main sponsor here, Railtech, and my faculty collaborators, graduate students, and undergraduate students for all their contributions. So with that, I would like to thank you for your time and attention, and I'll be happy to answer any questions.
Do we have any questions? Send the mic your way. We got to use this.
Thank you. Thank you very much for your presentation. It was very, very nice. I really like the work you guys are doing. I have a question. When you're talking about the ultimate load for your new high-strength concrete, You're comparing with which ultimate load? An ultimate load after a fatigue test, or just a regular ultimate load for concrete? Is the 34 kips you mentioned before?
The last slides, this one's?
Yeah, yeah.
This is after fatigue.
Yeah.
After 6 million cycles of fatigue, and the comparison is standard to reduced modulus when both went through the same testing. Okay. So both the standard had suffered 6 million cycles, and reduced modulus 6 million cycles of loading. So they went through the exact same procedure. Needless to say, these tests took about 3 months.
Yeah,
Maybe more than 3 months, about 4 months.
Dimitris, very interesting presentation indeed, and good research. I was interested from the aggregates point of view again.
Of course, yeah.
Looking at some of the results of the standard and the 3 other granites. And you showed some LA abrasion results, which basically measures toughness and the breakage potential of the aggregates. I was wondering if you had a chance to also measure surface textures in any way. Or actually, I was thinking about offering you to maybe run some of your aggregates through the image analyzer we have.
Oh, that'd
and
be fantastic.
quantify surface texture, angularity, those properties, which may shed some light to actually some of the modulus results differences. And
that will be
strength,
fantastic.
You know.
That will be fantastic.
Maybe we can
Absolutely.
understand better the mechanisms,
can-
bond strengths, and things like those.
How much of the aggregate do you need from each one?
Just a few
Okay.
of each, that's all.
They will be in the mail on Monday.
Perfect. All right. Thanks.
Appreciate that. Thank you.
More questions?
When we use the mic, questions are picked up, right? Yes. Yeah.
I have a lot of questions, but I'll ask one.
Okay.
Whenever you were in the plant looking at the stress, or
The strain.
how the stress or how the strains were changing, did you happen to look at any of the QA/QC of those specific ties to see if there was any differences, or moving forward, if you came to deploy that system, do you have any long-term vision of what that can go to do or what it can have on the time?
Well, Marcus, thank you for your question. It's maybe an hour answer, but I'll try to keep it short. This technology, I think the sky is the limit of what we can do with this. Okay, as I said, as I mentioned, this is a technology that's been developed for over 30 years. There's a company that produces the software and hardware. When it comes to plant implementation, we're looking into getting systems for true non-contact measurements. We did do some further digging why the differences, and I have not shown you some other results that I have, where some of the ties show even worse performance because of the way we fabricated, I guess, those ties. The old batch finished, so it was and then a new batch started. Old batch was not enough to fill the form, so it was poor compaction. I mean, it was poor practice. Of course, the company would never do this on a production level. Okay, so those ties, when we picked up those measurements and we did some further digging, we saw that there was indeed poor compaction. We did some coring. There was no concrete attached to the strand, and produced all sorts of irregularities. And again, I'm mentioning this is not the standard practice of the company. This was just the specifics of this particular effort. It can be used for quality control, quality assurance, and within the month we'll have a paper out on this.
But did you happen to see a correlation between kind of stresses in the ties or from the forms that were maybe out of maintenance, or did you happen to see if anything?
So if there is any correlation between the ties,
If there was any distress, or they didn't get as high in a QA/QC test, or if the form happened to be actually out of nominal shape, if it was actually getting stuck on the
Yeah, we did some measurements. One of the things, I mean, we even picked up the formations of the cavity itself. Okay, as I said, these are like thousands and thousands of images. But when you look at the plant images, there was some skewness of the form, which indicated, I guess, non-equal distribution of the forces, which could be a result of the poor compaction, which could be due to anything. But again, this related only to the specific operation, and we had to do it in a way to satisfy the project needs. These were not production ties. Yet, all the HSRM ties passed the qualification tests. We've tested 32 of these in the lab, and we only got 8 of the standard ties. So the data that we have from the standard ties were limited. Okay, but we're getting more in, and we'll supplement our data.
Thank you, Professor Rizos, for the presentation. One question that I have, I don't know if you have the numbers of the ultimate displacement when you loaded those ties to failure after the fatigue tests.
Good question. I don't have them in here. I'll lie to you. I mean, this thing doesn't work as it used to. I should have my student Kevin here. I've been telling and bragging to everybody about him. He's my hard drive.
Just a quick question on the aggregate you used for the increased modulus. What's the comparative cost with regularly used aggregate? Is it about the same?
Actually, it's cheaper.
Cheaper? Okay. I would imagine
because
it's not as
it doesn't
meet the spec.
Exactly. Okay. So it's used for non-structural applications, just because it doesn't meet the specs, not for any other reason, because strength-wise, it's fine. So on a highway bridge, you don't want to have a member that it's designed for stiffness X and you have stiffness 2X, or half X, yeah.
I get a question. What about you've proven some benefits of a lower modulus cross tie? What are some other opportunities if we're not around an area that has some of the porous aggregate? Say we're out on the West Coast.
Mm-hmm.
What are some materials related, or mixed design, admixture options that we might have to try to take advantage of some of these findings?
This has been one of our thoughts here. What else can we do to reduce the modulus? The different mixes have been tried with rubber and other type of aggregates in it, or fly ash. These are all possibilities. Okay, so bottom line is that there are benefits in reducing the modulus of elasticity in the tie. We have not gone into these investigations yet with other types of aggregates, but we do have a list of things that we would like to try, as well as other applications, not just the tie, but we are also looking into other components of the infrastructure.
Any other questions? We have none from cyberspace, so I think we should give one more big round of applause to Dr. Rizos.
Thank you much. Appreciate for having me here and for the hospitality. Thanks, Riley.